Now let's talk a little bit about exercise 2.5. So if you look at this exercise and you're thinking, wow, I'm confused, I don't know what to do, then you are rightly so, because this is not exactly an easy exercise, but that's also good because this exercise really tests whether or not you have understood this whole problem about boundary value conditions, boundary value problems and boundary conditions. Okay, so in this exercise, let's just look at A. They say assume y of 0 equals alpha, and in the other endpoint L, we have that y of L plus gamma times y prime of L is equal to beta, where gamma is different from 0. And then they say find a finite difference approximation with truncation error big O of h squared. So find a finite difference approximation such that tau I is big O of h squared, and write, and then afterwards they say express the difference equation in matrix form and write up the difference equation in matrix form. And what they mean is write it up in the form that they use in the book on page 49. So write it up in matrix form, aka as A y equals z, such that when we have this, then all we need to do is just find the inverse of A and then multiply that over on this side, and then you have the finite difference solution. Okay, so we need to find a finite difference approximation that is big O of h squared. And then you kind of think, well, can't we just use the one we already have? But the problem is, the one we already have assumes that y0 equals y of 0 is equal to alpha, and that's good, but it also assumes that y of L is equal to beta. And that is something that is not satisfied here. So the whole purpose of this exercise is actually to find a way of coping when the boundary condition is not known very well. Or actually, a better way to express that is when the boundary condition is implicit and not explicitly defined. So it's implicitly defined. And what do I mean by implicitly defined? Well, the problem here is that when I try to draw my grid, well, before I could say this is 0, this is L, and I know that y of 0 is equal to alpha. For example, in this point here, this is alpha. And before I could also say, well, y of L is equal to beta, and then draw a point. So I had two very explicit boundary conditions. But I don't have that anymore. Because here, all I know is y of L plus something else is equal to beta, and this something else is quite unknown for me because I do not know what y prime of L is. So what do I do? Well, let's just recall our grid for a moment. This is xn plus 1, and this is equal to x0, and in between we have x1, 2, 3, 4, 5, 6, and so on, and so on. And if we look at pages 48 and 49, we already have a method that has a truncation error that is big O of h squared. So actually the method that is constructed in 2.2 already has the desired truncation error. So A given as, well, the formula 221, and Z given as, well, formula 220, already has truncation error that is big O of h squared, at least for all the points that are before this thing over here where it all just screws up. So how do I figure out what to do about this point? Actually, all I need to do is be able to approximate this using a finite difference formula that has a truncation error that is big O of h squared. And you might ask, well, why is that enough? When we actually, well, why is that enough? And the reason for that is theorem 2.3 in the book. And you can try to take a look at it and read it a bit. It more or less tells us that the difference between the finite difference approximation and the exact solution is upwardly bounded by the biggest of two things. One is the overall truncation error, and the other is the error that we have in the starting point 0 and in the ending point L. So basically what it means is if we already have a method that has truncation error big O of h squared for all the other points, then it's enough if we just also use a finite difference approximation for this endpoint that is also have a truncation error that is big O of h squared. And to do that, we use what we call a, well, let's see. Let's take a look at table 1.1 in the book, because there we have some different finite difference formulas. Trying to find the table. It's not here. It's not here. Here I have it. On my in my book, it's page 7. So what we see quite quickly already is we can't use the forward or backward difference formula because their truncation term is big O of h and not big O of h squared. And we can't use the centered one either because if I want to approximate y prime of L, this is y prime of x n plus 1, then if I use the centered one, I will need y of x n plus 2, and I don't have that, so I can't use that either. Now what can I use? The one I can use is the one-sided formula, because we can see that it has a truncation error that is big O of h squared, and also if, for example, if I look at the second one-sided difference formula, then I can actually approximate this by using y, so it's given by 3 times y of x n minus 4 times y of x n minus 1 plus y of x, oh sorry, this is not minus 1, just xn, and then, no. Why am I so bad at this? Let's try again. So this is by no means easy. Xn plus 1 here. Yeah. Minus 4 times y of xn plus y of xn minus 1. All of this divided by 2h, where h is the step size. So this is the one-sided formula, and if I try to replace that into this, and since I ditch my truncation term here, what happens is we go from the exact version to the version where I use the finite difference approximations. So what I have is y prime approximated in step n plus 1 is given by 3 yn plus 1 minus 4 yn plus yn minus 1 divided by 2h, and that plus y of L is equal to beta, and also I just add the approximate value in here. So this thing has a truncation error that is big O of h squared, and this is equal to beta. And based on this, I can see some stuff. So what can I see? First of all, if I try to isolate yn plus 1, so you guys try and isolate yn plus 1, then what happens? Then I have an expression of yn plus 1 on, for example, the right-hand side, and then I have yn plus 1 on this side, probably with some extra stuff. And then I will have something with yn and yn minus 1 on this side, probably with some extra stuff as well. And that extra stuff goes into the A matrix in the last line. So we do not change anything except for the last line, because it's in the last line that we work with something that has to do with this last boundary here. So the rest of this exercise is up to you guys. It's for you to play with, and if you encounter any problems, then just raise your hand and ask me. Anywho's, this is just the amount of hints that I will give you, and I hope you have fun.